Look around and you won't see it, but an unimaginable volume of data is racing across the globe right now. Military communications, financial markets, and the entire internet demand continuous, instantaneous transfer every millisecond. For decades, the standard highway for this information was copper. But pushing modern data volumes through solid metal creates a physical bottleneck. It's bulky, heavy, and difficult to manage at the scale the world now requires. Copper also has two distinct physical limitations. It acts like an antenna, making it vulnerable to electromagnetic interference that can scramble data, and the electrical signal naturally loses power the further it travels down the wire. To sustain global networks, engineers had to move away from heavy metals. They needed to transmit data using the fastest medium in the universe, light. Relying on light creates an immediate problem. According to the laws of physics, light naturally travels in perfectly straight lines. Our planet, however, does not. The Earth curves, oceans plunge into deep trenches, and city infrastructures are chaotic mazes of intersecting tunnels. This creates a direct conflict. We have to force that straight beam of light to curve with the ocean floor and snake through city pipes without letting a single photon escape into the dirt. The process starts by translating an electrical data signal into a light source, typically using an LED or a small laser. That light is fired directly into the core, a microscopic central strand of clear glass or plastic roughly the thickness of a human hair. But light won't just follow the tube on its own. It must enter the core at a precise angle, known as the acceptance angle, for the beam to successfully propagate down the strand. Even at the perfect angle, the photons will still bleed straight out the sides of the clear glass if they aren't contained by a boundary. To keep the signal trapped inside, engineers wrap the core in a second layer of glass called the cladding. The cladding is engineered to have a lower refractive index, meaning it is slightly less dense than the core it surrounds. That difference in density triggers total internal reflection. When the light hits the boundary between the two materials, it doesn't pass through. It reflects back inside, zigzagging down the length of the fiber. Finally, a thick outer coating, or protective jacket, is added to shield the delicate inner structure from moisture and physical damage. Under that jacket, the glass remains fragile. Fiber optic lines are more expensive to install than copper, and joining two ends together requires specialized splicing equipment to ensure the light path remains clear. By wrapping glass in glass and manipulating their densities, engineers transformed a brittle thread into an inescapable mirror trap for light. Not all trapped light serves the same purpose, however. Cables are built differently depending on how far the data needs to travel. Single-mode fiber features an incredibly tiny core, only 8 to 10 micrometers across, which forces the light into one strictly focused path. This focused path minimizes attenuation, or signal loss, making single-mode fiber the standard for communication across vast intercontinental distances. Multi-mode fiber uses a much wider core paths to travel at once. It is cheaper to produce, but because the light bounces erratically and fades quickly, it is only suitable for short distances, like inside a single building. The diameter of the glass core dictates the cable's purpose, balancing manufacturing costs against the physical limits of distance. At the end of its journey, the bouncing light exits the fiber and hits a photodetector. This device instantly translates the photons back into an electrical signal, completing a massive data transfer with almost no loss of information. Maintaining this network requires a massive industrial effort. Specialized ships are used to lower millions of miles of these microscopic glass threads onto the floors of our deepest oceans. The modern wireless world is mostly an illusion. Every signal we send is eventually dependent on a physical web of glass buried beneath our feet and our oceans. This high-bandwidth technology allowed telecommunications and cable TV networks to handle hundreds of simultaneous channels long before the modern web existed. The same geometry that carries data also guides light through twisting pathways, like a medical endoscope, allowing doctors to see inside a patient's body without invasive surgery. Because light signals are immune to electromagnetic interference, fiber optics are also essential for sensors in aerospace, heavy industrial automation, and military communication. By mastering the geometric angles of bouncing light, we engineered a shielded, interference-proof nervous system for the entire planet.